Okay, so it's now 10:30 at night. My family has just woken up, and so that gives me a shot to actually record this thing without waking them up. But I gave myself a little head start by drawing this stuff because it would take me a while to draw. But the topic of the day is what in the book says conic sections and polar coordinates. But really, kind of the topic of the day in my mind is eccentricity or eccentricity, like this. So let's look at this. These three conic sections. Here we have an ellipse. Here we have an hyperbola and a parabola. We can draw a directrix. Yesterday we only talked about the directrix being over here for the parabola, but really we could draw a directrix for any one of these. And more importantly than that, if I took some random point here, and I called that P, some random point um, on the line, and I drew two distances here. One of them is, I'm going to call this PF, because it's the point to the focus. And then this one up here I'm going to call PD for point to directrix. Likewise, this one will have the same thing. What if I draw a dash line here and a dash line there? Same deal here. This is the point. This distance here is point to directrix, and this distance here is point to focus, and the same deal in the parabola. Now we're going to define a new characteristic called eccentricity, and this is going to be pretty important for us. And E is defined as, the triple equals means defined, is the point to focus length over point to directrix length. Now if you recall from our drawings the other day, let me label some of these here in red, if I can keep the menu from popping up. The distance from the center to the focus, remember that distance is called C, and the distance all the way out to the vertex over here, I'm going to make that a solid line, and the distance all the way out to the vertex is called A. And recall that b squared was related to a squared and c squared. And this is c here, like that. So not only is the ratio of the point to the directrix and the point to the focus the eccentricity, but it works out that it's also c over a. So that's the distance to the focus over the distance to the vertex. And that's also the distance between. So I'll write that distance between the foci, one focus, two foci, over the distance between vertices. Okay, and that's called the eccentricity. Now, the way it works out is that for a parabola, PF equals PD, right? That was part of the definition of the parabola, is that the distance to the point is the same as the distance to the directrix. So we change that over here. PF equals PD. That was the first one we did. So if those are equal, that means the eccentricity is 1, exactly 1. Now for an ellipse, we know that, let's look at this, the distance to the focus is shorter than the distance to the vertex. So that means C is less than A, which means that C over A is less than 1, which means that the eccentricity is less than 1 for an ellipse. And if we have a hyperbola, we know that if we go here, that the distance to the focus, C, so this distance, is greater than the focus to the distance to the vertex. C is greater than A, which means that C over A is greater than 1, which means the eccentricity is greater than 1. Okay. Now this is tough to prove in Cartesian coordinates. So it's tough to show in Cartesian. So what about polar? Okay, so let's take a look at the polar coordinates here. I'm going to draw a generic conic section. So it could be a generic conic section. And I'm going to, I'll edit it. Okay, so here we are again. I just took some time to draw this. So this is a generic conic section. So this could be the right end of a right end of an ellipse. It could be a parabola, or it could be, you know, 1/2 of a hyperbola. The important thing is here that notice that I drew the focus is at the pole. Okay, so let's write this here in black. The focus is at the pole, all right, of the polar coordinates. So if I draw a generic point somewhere here, I don't know why that always happens in red, but it does. And so I draw this distance that goes like this, and then this distance that goes like this. And remember that here this is P. All right, so let's look at the eccentricity of this thing and kind of talk our way through it. The eccentricity, E, is going to be the distance PF over PD. So point to focus, well, point to focus here is really just R, right? So PF equals, that's just R. And then the distance to the, from the point all the way out to the directrix here, I'm going to define one more variable, and this is a new one that we're going to work with for now, is some distance k. So the distance to the directrix from this point is k, right, because I just have to go all the way k, minus the x value of this point. And if I define this, I'm going to have to make this pretty skinny here to get this in here. If I define this as theta, if that's theta, then this is our cosine theta. So the distance out there becomes k minus our cosine theta, right? And then so down here, I'm going to expand on this a little bit. I could solve, this is E. So then E becomes, well, no, what do I want to solve for? Sorry about that. I'm trying to look at my notes, which are on the other side of my desk. I want to solve for R, right? Because R is really what we're usually interested in. So R equals E times K minus R cos theta. And then I've got to distribute that E, get all the R's on one side, and I wind up with R equals EK over 1 plus e cosine of theta. All right, so that is the definition of a conic section in polar coordinates. The problem is we have this new variable k, which I'd rather not deal with, which is the distance to directrix. Okay. So let's look at a definition here, or a picture that will help clear things up a little bit. Let's see, where is our 11.7 for generic conics? Okay. So here we go. The one we just did was this, ke over 1 plus e cosine theta. If we did it the other way, if we flip things around algebraically, that would work out to be 1 minus e cosine theta. Likewise, if we wanted to go up and down instead of side to side, as you might expect, it would be a sine theta and a minus sine theta to get it to look like that. But nonetheless, we still have this k, and the question might be, can we get rid of k? All right, and I've got another drawing I'm going to see if I can fit on this page. Ellipse dimensions, can I fit that on there? No, not really. Yeah, that's not going to work. So, well, yeah, I'll just drag. I'm going to put this over here just so we can see it. Ellipse dimensions, okay. So now here's kind of a picture of an ellipse. Remember that A is the vertex, right? C is the distance to the focus, but C is, or the eccentricity is C over A. So let's write that down. Eccentricity equals C over A. So if I want to solve for C, I could just call it EA. And this is A, and then we could do some algebra and figure out that the distance to the directrix, if we drew in a generic point here and drew the distances, we could find out that this is A over E. Now if we can say that K, what is K? If this is the origin here, remember this is not the origin, this is the center of the ellipse, the focus is at the pole, or the origin. So that K really equals, it's this distance, A over E, minus EA. Right, so I go all the way out to here, which is A over E, and I subtract EA. So this is really my K. And if I stick that in this equation, the equation I just figured out before, I could say R equals E times K, but I now know that's A over E minus EA. This looks like a mess, but trust me, it'll clean up. Over 1 plus E cos theta. And then this boils down, after do a little bit of algebra, not much, to A times 1 minus E squared over 1 plus E cosine theta. All right. So this becomes a pretty important formula. In fact, it's going to be so important that I'm going to give it the red box. I'm going to give it a green box. This, and this is really the more important part of it over here. So this incorporates some fundamental dimensions: radius, which is the distance to the point; A, which is the semi-major axis of the ellipse; 1 minus E squared over 1 plus E cosine theta. So this kind of boils down our ellipse into all the important parameters that we really need to know. So it would be very similar Similar process for a vertical ellipse. All right. Now, if yesterday I mentioned about eccentricity and how the eccentricity affects the ellipse, I'll ask a question, and I will not answer this. What happens if the eccentricity is 0? Right? What would that thing look like there? So if E becomes 0, what happens to this whole thing? Let's think about that. All right, so that's really it for the ellipses, and this should get you pretty well on your way for most of the homework. But there are a couple of interesting little things that I'd like to point out about graphs and polar coordinates. The first one has to do with lines. Okay, and I'm going to make this a little bit bigger. Oop, I don't rotate it. I guess we got to go like that. I'm learning all sorts of new features about the tablet here as I do this. So now we're going to look at lines. All right, so what did I do here? Here I just drew some random line, okay, which I don't really know, just some line. And I drew, or I didn't draw, the book drew a point that goes, is the perpendicular line that goes from the origin to my line in question, all right? And I call this line from the origin to the perpendicular here, r sub 0. And then if I take just a generic point, r theta, right, generic point r theta, and I draw a right triangle here. So let me trace that right triangle in some other color, like in yellow. So this becomes a right triangle, right, and this over here that I drew over was an R. Okay. Well, this length here, r sub 0, really becomes r cosine of this angle here. And this angle is theta minus theta naught. So I can say that r sub 0 equals r times the cosine of theta minus theta naught, which means my equation for this line in generic polar coordinates becomes r equals, well, r sub 0 over cosine of theta minus theta naught. All right, so that's how we can get the equation of any straight line we want in polar coordinates. So if I can get the slope of it, if I can get the angle of it, that involves some tangents and some negative reciprocals, that kind of stuff, then we can get the equation of a line there. All right. The next topic I'm going to mention quickly is circles in polar coordinates. And before we do that, we have to very quickly review the law of cosines. And if we draw a generic triangle here like this, and recall this thing, how did I do it in my notes? Remember, the vertices of a triangle are capital letters, and then the small letters, the lowercase letters, go across from the corresponding vertex. So ABC like that. Now if I'm trying to find, for instance, A, if I'm trying to find this side, the law of cosine says A squared equals B squared plus C squared, right? Which looks a lot like the Pythagorean theorem. But since it's not a right angle, we have to adjust it. Minus 2 times B times C times the cosine of the corresponding angle. like that, 2bc cosine A. All right, so this is just the generic law of cosines. But if I insert a picture of polar circle here, okay, let's make that a little bigger. I think that leaves me enough room. Yeah, I think it does. So now, well, here's a similar generic looking triangle. If I know where my the center of my circle wants to be, or where I want the circle to be, and I call that the point naught or P naught, is R0 theta 0, right? R naught theta naught. I know my radius of my circle I want to be A, and so that leaves me with some generic point, R theta, right? Well, really I'm interested in an equation for R, or I actually know what I'm going to do is do it this way because I know this angle here. So I'm going to find the equation for A. So what do we write here? We write A squared equals the other two, R squared plus R naught squared minus 2R naught times the cosine of the angle that we're interested in, which is really this angle. So cosine of, and what angle is that? That's theta minus theta naught. Right? And via some algebra, we could shuffle this around and solve for R. But I think for now, I'm just going to leave it in this shape. So if we have, if we know the radius that we want, A, we know the original point, which is R naught and theta. So R naught, theta. So we know the coordinates of the center, we know the radius, we can come up with a formula for this. Some important things to remember that if theta naught is 0, right, then it just becomes R cosine theta, which is interesting. We've done some problems like that. If theta naught was pi over 2, so if we're trying to draw a circle here, right, then theta naught equals pi over 2. Well, we know that the cosine of theta minus theta pi over 2 is really the sine of theta, right? And so what happens when we have sine of theta? Well, we wind up with a circle up here. We've already done that. So this is a nice, we've developed some good tools to use for polar coordinates in a much more general case. Unfortunately, we're drawing to the end of this unit, end of the chapter. But for those of you going to electrical, civil, mechanical engineering, biomedical engineering, this will come up again, I guarantee it. So I hope this is a good introduction at least. And with that, I will bid you a good night.